is flat, so intramembranous can come in and divide the cartilage into pieces and form the flat part, and then the complex parts will be formed by the remnant of the cartilage. And then you have bones inside your head, like the sphenoid bone, that have greater wings and lesser wings, and the sella turcica, and you have all these foramen in it. That starts with a cartilage model, because it's got all these complexities. So you save the dermal bone for the simpler things, and the more complex bones you use cartilage model to start with. When the bone is starting to form, the cytoplasm of the osteoblasts will be, when the osteoblasts are just starting to secrete osteoid, the cells will pick up mostly red dye. But when they start to secrete more and more osteoid and then also calcify it, they have to have a very sophisticated endoplasmic reticulum, they have to have a sophisticated Golgi apparatus, and a lot of ER and Golgi. And so those organelles will pick up more basophilic dye, and the cell will now be bluer. So immature osteoblasts will be eosinophilic, but once they're secreting at a high rate, then they'll become more basophilic. As they secrete more osteoid and then calcify it, then blood vessels can penetrate. So there'll be an increase in vascularization of that dermal bone. Ultimately, osteoclasts come in and break the bone down, and then the osteoblasts have to lay down the mature bone. So it will end up looking spongy or compact. And when you look at the bone in a skeleton, you cut it and look at it, it looks exactly the same inside, whether it started in membrane or it started in cartilage. There will always be an ossification center, and so when you look at the bone as it's starting to form, to me, it reminds me of when you're in the lab and you're playing with bacteria. Well, you're not playing with them, but you're trying to culture bacteria. You get the bacteria and you place them on the agar, and then as the bacteria multiply, they kind of grow out away from that center. That's what's happening with dermal bone formation. There's a central area of ossification, and then you get little spicules, little struts of bone radiating out from that ossification center, and they eventually come together around blood vessels and form that woven bone. And that's what's shown here. So you have ossification centers with these struts of bone forming. Here's another ossification center. Eventually these will come together and you'll have the bone, the woven bone around a blood vessel. And so different blood vessels with woven bone around it. So the cells are secreting their osteoid and calcifying it. You have an immature bone form. Now you have to go back and remodel it into compact, form your osteons, and then trabecular, form those struts of bone. When you finally finish that, it will look just like endochondral bone formation. So here, early on, at 10 weeks, you see the cartilage models that are being set up in the fetus. The skull hasn't begun to ossify yet, so you see the developing brain in there. It's just a clear membrane. So all of this is going to develop via intramembranous ossification. So 6 weeks later, the bone has begun to form, The light yellow areas in the skull are where cartilage persists. There will always be cartilage in the head, but the cartilage is serving as a growth plate. So now it's kind of similar to the endochondral bone formation that we'll come to next. You need to have a way for the bones to increase in size as that brain that's in there is increasing in size. And your brain is looking pretty mature when you're born. It has all the basic structures there, and it has a lot of gyruses and sulcuses, and you've got all your lobes there. But you look at the size of the baby's head, and you look at the size of your head. The reason your head is bigger is because the brain is getting bigger. And you have to accommodate the size of the brain with the increased size of your skull. So you have cartilage, they call it fontanelles, little fountains of cartilage, that continue to form new cartilage that then can be ossified on the edges and allow the brain to expand. If the skull fused at 16 weeks, then the brain would stop developing, or it would herniate down into the spinal canal, and that would probably kill the fetus. So you need to allow the brain room for its continued growth. If you look at the lower extremity and then you look at the upper extremity, in both cases you have more ossification in the upper extremity than the lower extremity. If you look at the lower extremity, where is the patella? Patella is not there. Is this pathological? No, it is not. The patella does not develop until your baby can stand and put weight on its knees. When it starts to be able to bear weight and it stands and is able to ambulate a little bit, though that bending of the knee will cause, that repetitive bending of the knee will cause the patella to develop. That's why my definition of the patella is a sesamoid bone, because sesamoid bones develop in tendons. So your quadriceps tendon goes all the way to your tibia. There is no quadriceps tendon and then quadriceps ligament or patellar ligament in my class. Okay? So no knee until you can weight bear. You watch babies, what do they do first? They use their arms. Pull themselves up on their crib, pull themselves up on a table or a chair. They can get themselves standing, but as soon as they let go, they're going to plop right down because their lower extremities aren't ready for that weight bearing yet. Upper extremities ossify first. So upper, then lower extremity ossification. Also, if you look, the proximal part of the limb is more ossified than the distal part of the limb. So upper arm, lower arm bones are starting to ossify. Wrist is missing part of the metacarpals and the phalanges. They just have little granules of ossification occurring out there. And so it's proximal to distal ossification. So upper versus lower, upper occurs first, and then the proximal, both in upper and lower, will ossify before the distal. You look out here, nothing much has developed in the foot, but you've got the femur and you've got tibia form, and just a little bit of the fibula form. Okay, endochondral ossification, different from dermal because you set up a cartilage model first. It's usually made of hyaline cartilage, and the cartilage itself will have a perichondrium, and blood vessels will be attached to the perichondrium, but blood vessels cannot penetrate the cartilage. the cartilage is secreting a substance that will prevent the blood vessels from penetrating. As soon as you kill the cartilage, then the blood vessels can penetrate. So how do you kill cartilage? Well, you kill it by having the osteoblasts on the surface lay down some bone. And then the nutrients don't get to the cartilage except from the periphery. So some cells will survive, but the central cells that are most restricted in nutrient supply, they start to die. When they die, they can't secrete the substance that prevents blood vessels from entering. So the blood vessels on the surface penetrate and go into the area where the dead cells, cartilage cells are. The cellular periosteal cells will migrate in through the channel that the blood vessel made and line that channel. They'll be called endosteum then. And then they'll take up residence and start forming bone on the inside. Then that will also be endosteum. So cartilage model first. Cartilage will secrete a substance that keeps the blood vessels out, prevents them from coming in. Soon as you kill enough cells, then the blood vessel can penetrate. This first one that penetrates is referred to as a nutrient foramen. It is bringing nutrients into the center of the cell, but not to help the cartilage because the cartilage is on its way out. As soon as the bone is forming inside, then the other cartilage cells, they're surrounded by bone outside and inside, and the bone is not allowing nutrients to penetrate. So the cartilage will continue to die until you're left with just bone on the inside and bone on the outside. There'll be little bony spicules, just like in dermal bone formation, that will be most prominent at either end. And you'll be left with cartilage that is continuing to replicate, and this will be your metaphysis. And then these ends of the bone that are still cartilage will be your epiphyses. This will be your primary ossification center. Always in long bones, always occurs in the diaphysis first. And the epiphysis will be your secondary ossification center. So length of the bone increases at that epiphyseal cartilage that continues to proliferate. The new cartilage pushes the epiphysis away from the diaphysis. Actually occurring, the new cartilage is happening in the middle of the plate, and the older cells are secreting the matrix, which is pushing the epiphysis in one direction and pushing the diaphysis in the opposite direction. So you grow taller at these growth plates. The older cartilage cells that are on the edges of the epiphyseal plate will be accessible to the osteoblast. When the osteoblast lays bone or osteoid down on their surface, then they're going to die, and then that will be remodeled into bone. The closure of the epiphyseal plate depends on your genetic makeup. It also depends on whether or not you have spontaneous mutations of those genes that might interfere with your growth. Depends on your nutritional status. So you might be genetically predetermined to be 6'6", but if you don't have the adequate nutrients, you might end up 5'9", something like that. So there's a lot of things. If you are deficient in growth hormone, that could also interfere with your final size. Bone enlarges via apositional growth, What does that mean? It means that new bone can only be laid down on an exposed surface, on the outside or the inside. When you have bone that has already been formed, you can't get a osteoblast migrating into the matrix and then starting to secrete in the mineralized matrix. It's not going to get there in the first place. Even if it did, if it was transplanted in somehow, it can't push the matrix out because that's mineralized. It's hard as almost a rock. So the only new bone formation that can be induced to occur, you have to get space first. So osteoclast can come in and reabsorb bone, and then osteoblast can migrate in. Or you need to lay it down on an external surface or the internal surface. Secondary ossification, you have to kill the cartilage that was at either end. You do it in the same way you kill the cartilage in the diaphysis. Lay down a bony collar. So a new bony collar at either end. You start killing the cartilage. Can't prevent blood vessels from entering. So blood vessels penetrate and then start ossification at the epiphyses. Eventually, this will become spongy bone, and you'll be left with a growth plate that will continue to enlarge until you reach your genetically or nutritionally determined final height. At some point, the cartilage will cease to proliferate. So if you reach your final height, the genetic predetermined age, the cartilage cells will turn off. As they turn off and the older cells get ossified, eventually that growth plate will become solid bone. What is happening, you look up here, we've got a small light blue area surrounded by dark purple areas. The light blue area is where the cartilage cells are undergoing mitosis. So they will be close together. As they start to increase their Golgi and endoplasmic reticulum and begin to expand their cytoplasm, then the nucleus will be surrounded by lighter colored space. As they start to secrete matrix around themselves, then they will get further away from their neighbor. So you start with an area that the chondrocytes are multiplying, then they enlarge, then they start to secrete the matrix, and eventually the osteoblasts that are in the diaphyseal side will start to ossify the surface, and the cartilage will start to, the edges of the cartilage will start to get ossified. The cells die, and then osteoblasts and osteoclasts will remodel it into the bone, the trabecular bone. So different zones are summarized over here on the side. You start with the reserve cartilage, then the cells will proliferate, then you hypertrophy the cells, they get larger, more Golgi, more endoplasmic reticulum. Then the cells will get calcified, and then the bone will be remodeled and the mature bone deposition will occur. So here, child's hand and adult hand. You count the number of bones here. It's more than it's supposed to be because the bones haven't fused yet. You got little pieces of bone with a growth plate next to the bigger part of the bone, then another growth plate, and another epiphysis. So So if you look at these bones, here's the radius, here's the ulna. The radius looks like it's fractured, but it's not. That's the growth plate for the radius here. The wrist bones haven't completely ossified, so there's a lot of membrane between the bones. Here we've got the first metacarpal for the thumb. It looks like there might be a wrist bone out there, but that's the epiphysis of your metacarpal bone. And there's another one down below. These four bones have ossified proximally, but they're still growing distally. So they're almost ossified distally, but you can still see remnants of the growth plate. So they're still elongating. You get out to the phalanges, there's even less ossification. So again, ossification is occurring proximally to distally. So more ossification proximally, less ossification distally. When the bones finally reach their final growth, this growth plate will be replaced by a solid piece of bone. And you can see here there's a whiter area on right between a lighter and two darker areas on either side. So a lighter area, a whiter area, a whiter area, a whiter area. When you get that final ossification, it actually is a more solid bone. It's in the epiphysis, but it's not spongy bone. So that final ossification is a very dense bone formation. Okay, the bone growth in width, you have to have the ossification occurring around the existing blood vessels. So the osteoblasts in the periosteum will start to form layers that will start to get larger and larger and surround the blood vessel. If you look at the layers, they're not in concentric lamella yet. So they're kind of all going in different directions, but they've surrounded the blood vessel. So osteoclasts at this surface can start to reabsorb the bone there, and osteoclasts on the outer surface can start to reabsorb bone there. The osteoblasts will come back and go into the spaces that the osteoclasts have created, and then they'll start to form a concentric lamella. The first one, and then osteoclasts will work on the next part of the bone, and then osteoblasts can migrate in and secrete bone, and eventually you'll get your osteon forming. So you look at the bone in an infant, the marrow cavity is, you take that circle and move it over here, it's the same size, but in the adult, you're going to have reabsorbed where the arrows are, or in the child, and then to the adult, you'll reabsorb those lighter gray areas, and you'll remodel the cortical bone. You'll also be remodeling the trabecular bone that's in the center here. So eventually when you get to be an adult, the whole bone is enlarged, the marrow cavity is also enlarged. Okay, take a break and then we'll talk about this figure.